Hello, I hope everyone is doing well. We have gotten our information to the visual cortex. So I usually make a pretty big deal about getting to the cortex and this higher level processing in our cerebral cortex. If you remember, we talked about what the neurons respond to. So the neurons' receptive fields there in the visual cortex. We have simple cells, complex cells, and end-stopped cells. And if you need any review of that, you can go back to the retina and beyond to the very last piece of that where we go through those different kinds of cells in the visual cortex. And so we're going to continue talking about the cortex a little bit more, getting to the organization and structure of the visual cortex, and then going beyond the visual cortex as well, because right now we're experiencing features of the environment, but we want to put that information together into more complex things, right? Into tables and chairs and dogs and cats and people and faces and all of that. If you remember talking about the lateral geniculate nucleus having a retinotopic map, well, we're keeping that mapping that is on the retina, we keep that through the lateral geniculate nucleus and through the cortex. Except here, our retinotopic map is slightly displaced, but the neurons that are near each other in the cortex have receptive fields near each other on the retina. And this really allows for a kind of efficiency of functioning, right? That the things that are close together in space are close together on the retina, and they are still close together as we get to the higher level processing. The other thing we see here is cortical magnification. So we have this retinotopic map, but remember what's happening with those foveal cones, that they're getting the linear circuit and they're giving us that acuity. Well, this acuity plays out in a number of ways. One, that they have the representation in the brain, and so we can tell when there's a neuron firing, and then the one next to it is not firing, and then the one next to that is firing. It tells us exactly where those lights are. But now we also see part of how we get better acuity or better resolution is having more cortex devoted, more cortical space devoted to the fovea. So the fovea is 0.01% of the retina itself. That's how much space of the retina it is. But when we get it to the cortex, it's 8 to 10% of that retinotopic map. And this was determined through brain imagery, which we're going to see how this was done. Brain imaging technique that they used here was functional magnetic resonance imaging, or fMRI. You don't really need to know this or how this works, but it's good to think about it briefly and to realize that there are so many studies throughout the book and throughout the slides and everything that use fMRI. And they're basically using the MRI, the magnetic resonance imaging chamber, which uses magnetic fields and radio waves or radio frequency pulses, and then computerized enhancement to map out, get a very detailed map of the structures of the brain. And then with the functional, with the functional magnetic resonance imaging, they're using that MRI to measure the hemoglobin and where the hemoglobin is moving, where that blood is moving, and how much oxygen basically it has in it. Because hemoglobin has oxygen in it, it's bringing oxygen to these active areas, and hemoglobin also has that ferrous component. So if you've ever cut yourself and it tastes kind of metallic, right? So it lines up like little tiny magnets when it's in that magnetic field. And as we have these areas of high brain activity, blood flows here, and then that hemoglobin loses oxygen to the active neurons, because that's one of the things that they use when they're active. And then that causes them to respond differently or more strongly in the magnetic field. And so if you see this out in the world, out in the field, they usually call it fMRI, but they might also call it bold contrast imaging or blood oxygen level dependent imaging. Those all really mean the same thing. We're looking at where blood flows and where it's losing oxygen to see what neurons, what brain regions are active. And what an fMRI does is it measures measures relative activity in areas of the brain by detecting changes in the magnetic response of the hemoglobin. And when I say relative activity, what I mean is, so the brain is always active, and so we're going to have to subtract out something to show that relative activity, activity relative to something. And so this subtraction method, it has a certain logic to it that they usually have some kind of, so here's my experimental task, and here's my control task. And so they're subtracting out the brain activity to this control task. And you can always kind of ask, was this a good control task? Because otherwise we're just looking at brain activity, and there's brain activity all over the brain all the time to all kinds of things. And so it's not really that informative just on its own. I say that, but then we look at this, they don't tell us what our control task is here in the Doherty et al. Study. The Doherty et al. Study basically looks like this. I'm the participant. I'm looking at that circle in the middle, which is my fixation. So kind of like a fixation cross. I'm supposed to be looking at that. And they're shining a light either within the red area, which you can see is within 5 degrees of visual angle. If you remember me talking about visual angle, my foveal vision is the 0 degree point, and we move out from that just like a circle. So that within 5 degrees, I'm very close to the foveal vision, and you can see that that red area is smaller itself than the blue area. So the blue area, they shine a light out there, and they measure brain activity to that. And you can see that that's out past 10 degrees of visual angle. So it's out in the periphery. And what we can see in the brain, or what you can see there in the image of the brain, is that that red, even though it's smaller, out in the visual field. And so what would be happening at the retina? What's happening in the brain activity is it's actually in the visual cortex is it's actually more space, right? It's more cortical space responding to that little region that's closer into the fovea than that whole larger region that's out past 10 degrees of visual angle out in the periphery. Another kind of neat visual representation of this, of what we would be seeing in the brain, if we think about the fact, right, that what we're looking at when we are looking at that word periphery, and we're right at that red dot in periphery, you can kind of see surface area, the A from area, upside down, and it's above the word from the periphery, and that is inverted and flipped, right, and that it is magnified and more detailed there where our fovea, where we are putting our foveal vision. So cortical magnification, we need this extra cortical space when we have a task that requires that visual acuity. That's why we point our eyes to those letters when we're trying to read. Good acuity is associated with a sharp focus of the image on the retina, those foveal cones having that small amount of convergence, so the small amount of convergence of the cones, and then relatively large amount of cortex devoted to the fovea. And so people with more cortical space devoted to the fovea also have better acuity. And what do I mean by all of this? So my example that I usually use is to compare myself with my sister. She has very sharp long distance vision, and I have been myopic, so I've been nearsighted. They caught it when I was in first grade, and so I was about 6 years old, and they said, when they caught it, they said she's probably been legally blind for a while now. And so my visual system wasn't developing normally, and I never had that sharp focus of the image on the retina, which means the visual system didn't develop as a person who has a good sharp image, good focus of the image on the retina. And so I was walking with my sister, and I pointed up at a bird, and I said, you think that's a turkey vulture or a hawk? because you always want to see a hawk, right? But it was flying like a hawk. It wasn't doing the round and round thing like a turkey vulture. It was going straight um, across the sky over us. And she looked up for a second and she gave me this look like, "Are you kidding me?" She said, "Of course it's a turkey vulture. Look at the beak on that bird." I was like, I'm lucky to see a bird in the sky. I can't see the beak on that bird. And so there are never going to be glasses that help me to get to the long distance sharp vision that she has, because I just don't have the same amount of cortical space devoted to the fovea, because I never had that. I didn't have that sharp focus of the images on the retina when the visual system was developing. When we look at that retinotopic map with its slight displacement and talk about cortical magnification of the fovea, that larger area devoted to the fovea, we're really looking at the surface area of the cortex. So that's the mapping or structure of the surface area. But if we go below that surface area, if you remember, there were these columns in the lateral geniculate nucleus, and I said, just like, or there were these layers, and it showed us columns, and so just like that, we have 6 layers in our cortex. There are 6 layers to the cortex, and so if we look at a particular place and we choose a point and go perpendicular into a column, we're going to hit a location column that within that has orientation columns and ocular dominance columns. And I'm going to explain these. Perpendicular to the surface, so again, if you kind of look straight forward and you kind of think of what's up, and you can even put your finger up in your right, so the right visual space up above yourself, that's going to hit on the lower left side of the visual cortex. And so if you go, and that's our retinotopic map, but if you go perpendicular, if we put an electrode in and go perpendicular to the surface, we're going to see that at that point, all of those neurons in those various layers within that location are going to have their receptive fields at that same location on the retina. So that we have location columns. Within those location columns, we have orientation columns. So if we look at A and B and think about within that, we have, putting those together, that would be a location column. We're going to go from horizontal, and as we move across the surface of the cortex, we're going to go through various levels of oblique, and then we're going to get to vertical. And so we have those simple cells responding to particular orientations, and they're lined up in these various orientations. So if I'm at this lower left part of my visual cortex and I'm measuring, it's going to be a particular location up in the upper right visual field, and that first electrode is going to hit a particular orientation. And if we move it just slightly, we're going to hit a different orientation at that same location until we get to a new location as we move too far away. I hope that makes some sense. And we also have ocular dominance columns. So within a location column, we're going to have an ocular dominance column where basically the neurons are responding better to the right eye versus the left eye. And next to that, we're going to have an ocular dominance column where those neurons are responding better to the left eye than the right eye. So most neurons respond to stimulation of both the left and right eyes, but most neurons respond better to one eye or the other. And so we do have this ocular dominance. And finally, this is visualized kind of like this as a hypercolumn. Now you did see, if you did notice that there was this bend or fold, the cerebral cortex it has a lot of bends and folds, right? It has lots of gyri and sulci, as the gyri come out and the sulci go in these bends and folds. And that is to give us more surface area for more neurons in our cerebral cortex, because we are humans and we're quite intelligent. And so we need more surface area for those neurons. So the Hypercolumns don't actually look like this, but this is how they were visualized originally as these blocks, but they are going to be kind of squished around. That's all. So they won't be blocks. They'll be more squished around in a funny shape. But anyway, if you kind of look there, we're in a location column. So the white area is going to be a hypercolumn in a location next to the blue area, which is going to be a hypercolumn of the location next to that, right? So that's kind of how our retinotopic map is working. And so the hypercolumns are made up of a location columns, orientation columns within that. You can see that kind of going, if you think about the z-axis, they're going back that way, and we're going to have our various orientations of line, those neurons that are responding to vertical lines, oblique lines, horizontal lines at that particular location. We have those ocular dominance columns, which are labeled there as R for right and L for left. And I will say we also see within those spatial frequency columns, which your textbook leaves out, and he's left out since I've taught this class, but honestly, there's a lot of research that looks at spatial frequency and whether something looks blurry and it has a larger spatial frequency, or there's lots of fine detail and there's smaller spatial frequency. It's kind of important if you're reading in the field, so I hate to just skip it, but you don't have to know it because your author doesn't talk about it. So if we think about how an object is represented in V1, or the primary visual cortex, that we are representing these features at particular locations. Persons looking at a tree, we get the image of the tree on the retina. Representation in striate cortex, or the V1, is similar to the retina, except we have more of space, more cortical space devoted to the fixation point, or the fovea. We might start asking that question: how does this electrical activity really stand for the object in the environment? So this is the first place where we're going to really talk about this mind-body problem, which at this point seems like a problem, right? Because everything's pulled apart into these locations and these features. We've actually, if you remember, we took that visual information apart and turned it, basically smashed it into dust, into little tiny dots, and then we put it back together into these features in the visual cortex, or in V1. So if we're looking at something like a tree trunk, choosing something really simple that's basically a large vertical line, you can see that we're going to have these location columns, which is what A, B, and C are showing, these separate location columns or hypercolumns. And then within that, there's going to be an orientation column that is responding. The orientation column that is responding to vertical lines is going to be the column that is now responding. And these are going to be separated in the brain in this way, in such a way that we are now representing the stimulus in a really different manner, that we cannot say this cortical representation is resembling the stimulus. Right? The representation of the tree trunk and the visual cortex, this is the first step. And we need to put this information back together to see that this is a tree trunk and not these separated out vertical bars. What the mind-body problem is it's this problem of how these physical properties, like nerve impulses or sodium and potassium ions flowing across a membrane, how do those physical properties, how do the physics transform into this perceptual experience, the richness of our perceptual experience? I do have this as a blue question. I'll let you think about that while my dogs bark over me a bit. So pause here. Think about this. Think about whether or not you feel like, of course, they represent or transform into the richness of our perceptual experience. I feel like that makes a lot of sense. Or not. Maybe you don't. So this is the hard problem of consciousness that we're asking about or talking about, where the easy problem of consciousness is how do physiological responses correlate with experience? And when we look at something like that fMRI study, we can see, hey, here's this correlation. They shine a light in this red area. We see the visual cortex activate in these regions, and so we see that relationship, right, or that correlation. But the hard problem of consciousness is how do those physiological responses cause our experience? How do neural impulses become the perception of my grandmother's face, the experience of the color red, not just seeing perceptually the color red, but the emotions and everything that gets to be part of the color red for us, or the feeling of a bitter cold wind. And I'm going to come back to our question in another way, or said another way, that when we are looking at something like brain activity in response to some task or in response to some emotion or some perception, are we addressing the easy problem of consciousness? So how does the physiological response correlate with experience? What is that relationship? Or are we addressing the hard problem of consciousness, which is the question of how those physiological responses become the perception of a tree in this case? And I like to use the example of my grandmother's sticky buns, and because smell has such a powerful influence over our emotional memories. And I can smell, or when my mom was alive and she'd make my grandmother's sticky buns, which then became really my mother's sticky buns, but they were always something I remembered about my grandmother. And I'd walk into my mom's house, it would just transform me back. I would just go back in my mind. It would be like I was at my grandmother's house, and I could see her in the kitchen. I know where my grandfather is in that back room. I know where the bedrooms are and the playroom and outside with the crabapple tree in the woods. And all of that kind of comes rushing back when I smell that smell, or when I used to smell that smell. Now I just talk about it, since I don't have that recipe. But you guys make something, or a lot of Southern people make something similar called monkey bread. So maybe I should try to make that sometime. But it just transforms me back to that time, and it's a very kind of emotional memory for me. My grandparents have been gone a long time. The last time I saw my grandmother was in 1982, I think. And so it's incredible to me that there is this connection between, hey, I have this smell, and then I have this really vivid and emotional kind of experience in relationship to that smell. And so that physiological response becomes this complex bunch of perception and emotion and memory. That is, I think, a fascinating and complex question, and you can probably come up with many examples from your own life of that, how those neural networks must be working to give you the perceptual experience that you have for certain things, especially. But again, pause, think about it. This is a great place to end our discussion of the visual cortex.